Hello, and welcome back to the course on Physics for Engineers. So we are still on chapter 8 of this course. So before we proceed, let us first review what we have discussed in the previous chapter. So we have discussed about waves and periodic motion, and that and we define the relationship between the frequency and the period to be inversely proportional. And also, we define a quantity called angular frequency, which is just 2 pi times the period, or 2 pi times the frequency, or 2 pi over the period. So for this lesson, we will be talking about simple harmonic motions and damped oscillations. So what is simple harmonic motion? So it's basically the oscillations where the restoring force is directly proportional to the displacement from the equilibrium. So the displacement can be along the x-axis, the y-axis, or z-axis. So in this case, our displacement is along the y. So the relationship of the restoring force and the displacement is given by Hooke's law. And the K here, the proportionality constant, is just what we call the force constant. So the direction of the force, the restoring force, is actually opposite of the displacement. So when this mass here is being displaced upward, the restoring force is actually downward. So the restoring force is the force that makes the object, the oscillating object, return to the normal or equilibrium position. So when the object or the mass is being displaced downwards, the direction of the restoring force is upward. So it's always directed opposite of the direction of motion. That is the negative sign here. So we have actually, I've actually shown you what a simple harmonic motion looks like. So I have presented you this animation before. So this is basically simple harmonic motion. So the amplitude of the wave is the same at all times. So that one. So this is simple harmonic motion. So for a spring with force constant K and mass m, the angular velocity of that spring, which is originally 2 pi times the frequency, will now be square root of K over m, where K is the force constant and m is the mass of the object doing a simple harmonic motion. So since the frequency is just related to the angular frequency by a factor of 2 pi, and so the frequency is just this one, 1 over 2 pi square root of K over m. And the period is in the inverse of this, so you have 2 pi square root of m over K. If you have a simple pendulum, a pendulum that vibrates at a very small angle or very small oscillation, very small amplitude, the force constant is just equivalent to mg, basically the weight over the length. Weight over the length. So if your oscillation has dissipative or damping forces such as friction, we call that oscillation as a damped oscillation. And in damped oscillation, the amplitude of oscillation is actually decreasing. So the angular frequency of damped oscillations will now have a term, an extra term, under the square root, which is minus b squared over 4m squared. So b here is what we call the damping constant. It depends on the system, the situation. So a condition called underdamping happens when the oscillation has a steadily decreasing amplitude. And this is due to a very weak damping force. And a situation called overdamping, wherein there's no oscillation and the system slowly returns to equilibrium. And this is due to a very strong damping force. Now, there's a critical limit wherein K over M is equal to B squared over 4M squared, wherein the angular frequency is 0. There's no angular frequency, so meaning there's no oscillation. So in that case, that's what we call critical damping, and the system returns quickly to equilibrium. So again, this is simple harmonic motion with no damping, and this is these are scenarios of damped oscillation. So the red curve here, the red curve that you see is an underdamping or underdamped oscillation. The blue one, you will notice that there's no oscillation after this time period or this period, but the system slowly returns to equilibrium. And in critical damping, the green curve, the system quickly returns to equilibrium. So no oscillation at all. Okay. So let's have an example. So this is simple harmonic motion of an old tricycle, in an old tricycle. So maybe you have experienced this when you ride an old tricycle, that the tricycle is moving up and down whenever whenever it's just on a level road or on a bumpy road. So in this example, the shock absorbers of an old 500 kilogram tricycle are completely worn out, such that when 3 persons, a driver and 2 passengers, with combined weight of 1,500 Newton, rides the tricycle, it drops by 4 centimeters. So when the tricycle goes through a rough road, it starts oscillating up and down in simple harmonic motion. So treating the tricycle and the persons as one mass, find the period and frequency of the oscillation. So basically, it's like you're running a bumpy road. That's actually a simple harmonic motion. Okay, so we need to know the mass of the person first and the mass of the tricycle which is given, so to get the total mass, because we will treat this system as one mass. So we need to solve for the mass of the person. So we are only given the weight of all of the persons, so combined weight. So to get the mass, we divide it by G, or 9.8, and we get 153.1 kilograms. So therefore, the total mass, the mass of the persons plus the mass of the tricycle, is 653.1 kilograms. So we now solve for K. So take note, in our formulas, in order to solve for the frequency in the period, we need to solve for the force constant. And the force constant is just given by the restoring force, the ratio of the restoring force, and the displacement. So in this case, our restoring force is just equivalent to the weight. By virtue of Newton's third law of motion, the restoring force is just equivalent to the weight of the passengers in this case. So you will have 1,500 Newton divided by the displacement. So the tricycle drops by 4 centimeter. So that's the displacement. So you will get K of 37,500 Newtons per meter. So that one. So to solve for the period, you just use the formula 2 pi square root of m over k. We already know the mass. We already know the k is force constant. And we get a period of 0.83 seconds. And for the frequency, we can use the formula, or we can use the value of the period here, 1 over 0.83. And we still get the same answer of 1.2 hertz. So that's how we solve this problem. Simple harmonic motion applied to an actual scenario. So let's have another example. For example, simple pendulum. So a simple pendulum is actually a pendulum wherein the amplitude is very small and it's a length L. So when you say the amplitude is very small, meaning it's just very small swings, not very wide swings. Because if you have a very wide swing, it's no longer a simple pendulum. So what are the frequency and period if your simple pendulum has a length of 50 centimeters? So for a simple pendulum, the force constant is just the weight over the length, mg over L. So we substitute that in our equations. So when you substitute K here by mg over L, you will notice that M will cancel each other, will cancel. And these are your new equations for the frequency and period for a simple pendulum. So you will notice that the mass actually doesn't matter. So you are actually not given the mass here because it actually doesn't matter if you only have a simple pendulum. A pendulum with a very small amplitude of oscillation. If you now have very large swing of your pendulum, then the mass will actually matter. So in this case, this is just a simple pendulum. So the mass of the object swinging actually doesn't matter yet. So substituting all of the values, so the length is 0.50 meters. So always convert your given values to standard units. So you will get a frequency of 0.70 hertz. And for the period, 1.42 seconds. So again, you can solve for the period by just taking the inverse of the frequency, 1 over the frequency, and you will get the same result. So that is it for the lesson on simple harmonic motion and damped oscillations. So I will see you again in the next lesson. So bye for now.